In this video we will look at, or this video presents, I should say, some recent solutions to the Snellius-Pothenot problem from surveying that use geometric algebra. And here's the problem statement. In this situation here, there's a surveyor at point P, an unknown point, who wants to establish the location of that point by shooting bearings to three known points A, B, and C. So the first solution, or the first solutions that we'll look at here, were published recently in the Journal of Geodesy, and this is an open source article. It's, of course, you can access it free, and I will put the link in the video description. The second solution that we'll look at is an improvement to one of them that's published in this article. So we'll just scroll through this briefly. You'll want to look at it in detail yourself, I suppose. So we'll just scroll through here. There's motivation, background literature review, of course, and the contributions that this article makes, and a review of some basic concepts of geometric algebra. And the first solution is by Euclidean vector geometric algebra, which they will call VGA. It's kind of the plain vanilla version of geometric algebra. And the second solution is by conformal geometric algebra, which is quite an overpowered technique for a problem like this, at least in the two-dimensional form. But this article will help to show how to use it also for three-dimensional problems. So these authors are really quite thorough. They go through this, traditional methods, the vector geometric algebra solution, which is the one that we will show an improvement on later, and then the conformal method. So here is the conformal method. They also go into the three-dimensional form of it. Which you really do want to use conformal for a problem like that, or probably some people say projective. They go into situations where the solutions do not work. They do numerical simulations and benchmarking of the speed of the algorithms. And these authors pay a lot of attention to uncertainty analyses. And they have kind of a novel way of displaying the areas or the locations of the unknown point P that cause most problems in terms of uncertainties. So I hope that you'll take a look at that article. It does require a bit of study. Now we will switch to the other solution, which again is an improvement, I believe, on the vector geometric one. So here again, whoops, wrong slide. We'll come to that later. Again, here is the problem statement that we looked at. This article, or this improved solution for the two-dimensional case, is available on Vixra, and I will link that. It begins with the ideas that we will use, and I'll go back to this. The main ideas that we'll use are rotations of vectors and reflections. And reflections are very easily calculated in geometric algebra. For example, the reflection of the vector q with respect to t is this vector q prime. And all that's needed to calculate q prime here is to form the product t times q times inverse of t. Very simple. So first, the problem is formulated in geometric algebra terms. Now, what's kind of different here is that the first step will be to find the center of the circle that passes through the unknown points A and C, or the known points A and C rather, and the unknown P. And what we will do then is rotate AP until it coincides with BP, and we will rotate CP until it coincides with BP. And from the formulas for the rotations, we will obtain formulas for the result, the vector from the center here to P. So this is the solution strategy that I just described, and now we'll go into the solution. The first step is to determine the location of the center of that circle, which is simple, but this document goes into some justifications of why this simple formula works in different situations. And after finding that center, we get down to using the rotations. I'll go back to that. Got just a little bit out of sequence here. Finding the vector 2p via an analysis of the rotation a minus p. So that is this rotation, a minus p, rotated into b here. And if we work through that, we come fairly quickly to this expression here, which we can transform very easily into an even simpler one. And we have identified a vector WA with respect to which P is the rotation of A. And the article goes into why this is. It's quite simple, really. Now, the same thing can be done rotating C minus P until it coincides with B minus P, and we get a solution that's to some degree independent. And we'll see how to do that here. Again, it's not difficult at all. So we end up here with the vector P being the reflection with respect to WC of the vector C itself. So this is the formula for the reflection here. P is WC times the vector C itself times the inverse of WC. And of course, just looking at this on the screen, it goes kind of fast, but the calculations and the manipulations are not at all difficult, and it ends up being quite a simple solution. And of course, we want to test out that solution. So there's available a GeoGebra construction, which is also linked in the video description. There's a description here of the solution itself and the notation. And here we have the known points A, B, and C, the unknown P, and the solution that's based upon the angle between AP and BP. And we can test to show that even if we move P around to different positions with respect to A, B, and C, this solution still does work. Similarly, this construction lets you test the solution that's based upon the angle beta. And here again, the vector from the center of that circle, 2P, is reflection of the vector from the center to C with respect to this vector WC. So I hope that you'll check these out and that you'll play around with the GeoGebra confirmation of the solution, and that you'll also consider joining the LinkedIn group Pre-University Geometric Algebra videos, or the LinkedIn group is just Pre-University Geometric Algebra. And I hope that you'll consider checking that out. That group is dedicated to providing materials for teaching geometric algebra. Thank you for your time.